In this video, I'm going to briefly introduce you to the Fourier transform. Signals that are not periodic can be represented as a function of frequency using the Fourier transform. So this is really useful because we can take a time domain signal and represent it instead of in the time domain we can look at the frequency content of that signal. We represent the Fourier transform as capital F of omega, and we would write that as saying that f of t can be transformed by the Fourier transform, which is a big fancy looking f, to big F of omega, the Fourier transform. We calculate the Fourier transform as f of omega is equal to the integral from minus infinity to infinity of f of t e to the minus j omega t dt. Now I know I'm going from time domain to frequency domain because I'm going to integrate out over all time t, the time. So I'm going from minus infinity to infinity, and I'm integrating with respect to t. I'm going to get rid of the time. On the other hand, I can come back from the frequency domain to the time domain by taking the integral 1 over 2 pi of 1 over 2 pi times the integral minus infinity to infinity big F of omega e to the j omega t d omega. And you can see that again I'm going to be integrating out all of frequency or omega to get back to the time domain. So I call that the inverse Fourier transform. Now we can plot the spectrum of f of omega. In general, the signal is complex. The signal f of omega is complex, so we have both a magnitude and a phase or angle spectrum. We can write f of omega, we can break it up into a magnitude and phase component. So it would be the magnitude of f of omega multiplied by e to the j angle f of omega. So that has a magnitude and a phase angle. Note that if f of t is real valued, then f of minus omega is equal to negative infinity to infinity integral of f of t e to the j omega t dt. As a result of that, the magnitude of f of omega is represented as an even function, and the angle of f of omega is an odd function. So in drawing, what that means is that f of minus omega is equal to f of omega, whereas the angle of f of minus omega is equal to the minus the angle of f of omega, or an odd function. Alright, so we're going to take one example where we would find the Fourier transform of e to the minus at u of t using the definition of the Fourier transform. Alright, in general what we'll find is that there are some common Fourier transforms we care about, and for that you will get Fourier transform tables to use. So by definition, f of omega is equal to the integral from minus infinity to infinity of f of t, in this case e to the minus at u of t, times e to the minus j omega t dt. What I can do is realize that u of t is equal to 1 as long as t is bigger than 0. So I can change my bottom limit of integration to 0, leave my upper limit the same, and then I can smush e to the minus at and e to the minus j omega t together and integrate with respect to t. Now, when I perform this integral, I should get negative 1 over a plus j omega e to the minus a plus j omega, all in one quantity, times t, evaluated between 0 and infinity. Now, let's keep this in mind. The magnitude of e to the minus j omega t is equal to 1. So, to know where this goes as t goes to infinity, we have to look at what the value of a is. So it turns out that as t goes to infinity, e to the minus at, e to the minus j omega t is equal to infinity if a is less than 0. That means that a here would be less than 0, so I get e to the positive value as t goes to infinity. That goes to infinity. However, if a is greater than 0, then what I get is 0. Okay, so as long as a is greater than 0, this is going to converge to 1 over a plus j omega. Now that's technically the answer. That is the Fourier transform, but I'd also like to draw the spectrum. We can express, to do this, a plus j omega in polar form. All right, this is common. We know how to write a complex number in polar form. I take the square root of a squared plus omega squared. That's my magnitude. And then I know that the angle is going to be the inverse tangent of omega over a. All right, so that means this is going to be the square root of a squared plus omega squared multiplied by e to the j inverse tangent of omega over a. Now, I realize that's on the bottom of my fraction, so f of omega is going to be 1 over what I just found, and I know that if I would like this exponent to be pulled up, I can just change the sign. All right, so what that means then, if I take the magnitude, is that the thing over on the left is the magnitude, and the angle is the negative inverse tangent of omega over a. Now, I'm not going to be too specific on how I get this, but I want to show you what the spectra are going to look like. So you start with f of t, e to the minus at u of t, drawn in red at the top, and then through the Fourier transform, what I get is the magnitude of f of omega, which you can see above, comes from here, and it's going to have sort of a Gaussian shape, and it's going to be an even function. On the other hand, the angle of f of omega, which comes from the negative of the inverse tangent of omega over a, is going to go between pi over 2 and minus pi over 2. And it looks like an odd function. So that's what I should expect based on the definitions we've discussed already. So let's talk about whether or not the Fourier transform exists. So there are some conditions that are called Darish conditions that say that if I have a signal x of t satisfying those conditions, then the Fourier transform is guaranteed to converge within some region. It could, like we had above, have some bounds on the roots. All right, but if the signal x of t satisfies certain conditions, which are called Darish conditions, the Fourier transform is guaranteed to converge. Basically, these conditions add up to the understanding that if a signal physically exists, then the Fourier transform also exists. So these conditions are as follows. First one, x of t is absolutely integrable. This means that if I take the integral from minus infinity to infinity of the absolute value of x of t with respect to t, that's less than infinity, meaning that it's finite. Condition 2, x of t has a finite number of finite discontinuities on a finite interval. So if I take an interval which is measurable, say 0 to 1, and I look in it, then the number of times that the signal is discontinuous is countable. I can count those number of discontinuities, so this makes it look like a real signal. And finally, x of t has a finite number of minima and maxima on a finite interval. So if I take, again, a finite set, something that has a start and a stop, in here can I count the number of minima and maxima? All these things imply the signal is a real signal, and so if I have a real signal, then I should be able to take the Fourier transform. What's the physical meaning of the Fourier transform? Well, it is the spectral density per unit bandwidth. It's kind of like a histogram for frequency. The amount of signal content at each frequency is displayed as the magnitude, and the phase of the signal at that frequency is displayed as the angle. All right, let's do one more example. Finally, let's prove that prove that if f of t is an even function of t, then f of omega is equal to 2 times the integral from 0 to infinity of f of t cosine omega t dt. Now this looks maybe a little challenging. It doesn't look quite like what we're expecting. So let's start with the definition of the Fourier transform. I know by definition that f of omega is equal to minus infinity to infinity integral of f of t e to the minus j omega t dt. If I use Euler's identity, I can break the exponential up into cosine omega t minus j sine omega t. And so that gives me two integrals. It gives me f of t times cosine minus j sine times f of t. And I'm going to call the first one expression 1 and the second one expression 2. Since f of t is even and sine of omega t is odd, then term 2 goes to 0. An even function multiplied by an odd function is 0. Since f of t is even and cosine omega t is also even, then f of t cosine omega t is also even. If you take two even things and multiply them together, you get an even thing. It's just like numbers. Finally, as a result, that means that since it's even, that means it's the same from negative infinity to 0 as it is from 0 to infinity. So this integral can be executed from 0 to infinity and just multiplied by 2. And that's what we were asked to show in the first place. So as a result, f of omega is equal to 2 integral from 0 to infinity f of t cosine omega t dt in the event that f of t is an even function. And that's all you need to know for a general introduction to the Fourier transform.